In this video, we're going to discuss the interconversion of carboxylic acid derivatives, or in other words, we're going to discuss how to turn one carboxylic acid derivative into another. So the first thing we need to talk about is that there is kind of a rule to these interconversions, and the rule is in reference to the relative reactivities of these carboxylic acid derivatives. So on the left-hand side, we have our acid chloride, which is our most reactive. On the right-hand side, we have the amide, which is our least reactive. So it makes sense that something that is very reactive, such as the acid chloride, could be turned into many other things very easily, and that something that's less reactive, such as the amide, would be pretty difficult to turn into other compounds. And so the general rule that we're going to find is that if you write this list out from most reactive to least reactive, from left to right, you can always go from something that's more reactive, such as the acid chloride, to something less reactive, such as the anhydride. You can also turn the acid chloride into an ester in one step, or into an amide. Similarly, we can turn the acid anhydride into an ester in one step, or into an amide. And we can also turn an ester into an amide in one step. But what we cannot do is go the opposite direction. You cannot take something that is less reactive and more stable and turn it into something that is more reactive and less stable. So going left to right in one step is not a possibility. So then what are we supposed to do if our goal is to take an amide and turn it into an acid chloride? We already said that we can't go there in one step. So what do they have in common? Is there a molecule that could join these two together? Hopefully what you're thinking of is these are both carboxylic acid derivatives, which means they can both be made from carboxylic acids and they can both be returned to a carboxylic acid. So we can take our amide and hydrolyze it in acid or base, whatever you wanted to do, as long as there is plenty of heat. And that would get us to our carboxylic acid. You can then react your carboxylic acid with thionyl chloride to get to the acid chloride. So you can go from right to left, from less reactive to more reactive, as long as you go through the carboxylic acid in between. And this rule only applies if everything to the left that has nothing to do with the changing identity of the leaving group is unchanged. If you want to do some chemistry on the left-hand side, that obviously involves some additional steps. So let's start with our most reactive carboxylic acid derivative. We can take an acid chloride and turn it into any other carboxylic acid derivative in one step. So for example, if we take our acid chloride and react it with a carboxylate, or even with a carboxylic acid, we can create an acid anhydride. We can react an acyl chloride with an alcohol in the presence of some base to create an ester. We can take an acid chloride and react it with an amine, and we would end up with an amide. Now the key thing about the amide reactions is that you can do this with a primary or a secondary amine, but you cannot do it with a tertiary amine, because if we do a reaction with the tertiary amine, we would have one other thing attached to here and a positive charge that we could not reconcile. So we can do this with primary or secondary because we can eventually deprotonate. Acid anhydrides are also very reactive, and so they can be pretty easily turned into other things. For example, if you react an acid anhydride with an alcohol, you can replace the leaving group with an alkoxyl group, which would give you an ester. Now, the important thing to note here is that you also have a pretty significant organic product from your leaving group. Oops. Which would be another carboxylic acid. But if you're doing this synthesis, the ester would be the object you're trying to get to. We can also add in an excess of an amine. Again, same rules. You can do this with a primary or a secondary. And you're going to have an excess that you can do the deprotonation. And you will end up with an amide. As well as a carboxylate side product. Esters have an extra trick up their sleeves. You can actually react an ester with a alcohol of a different identity. So instead of R prime, we have R double prime in acid. And going through the same mechanism as Fischer esterification, you can accomplish what's called a transesterification, where you turn one ester into a different ester. There aren't a lot of reasons that you would probably do this reaction, but it's actually often a side reaction that you have to keep in mind. We can also react an ester with an amine. Again, keep in mind that we're only doing this with a primary or secondary amine. You're going to want to have an excess so you can deprotonate the final product. And that would get you to an amide. Now, amides can't be turned into a lot of things. You can't turn them into esters or anhydrides or acyl chlorides in one step, but you can do some pretty cool chemistry with some drying reagents in order to create a nitrile. So these are the types of reactions that you can file away in the back of your head, make a flashcard. They're pretty straightforward. Now let's take a look at some fun problems. In this first problem, we have an acid anhydride that is being reacted with a mixture of ammonia and water and heat. So the question is, what's going to happen in this first step? What you'll find is actually that the ammonia is going to attack one of the carbonyls, and we're going to end up breaking open this anhydride. Step 2 is giving us a proton source so we can protonate our product. So let's group steps 1 and 2 together. We're going to end up with an amide and a carboxylic acid in the same molecule. Now, you can actually react an amine with a carboxylic acid and create an amide. If you couldn't, then we wouldn't be able to create proteins, right? The key thing about proteins and forming a peptide bond is that you have an enzyme where the active site is keeping the amine and the carboxylic acid close together and is catalyzing the reaction. In this case, we have kind of a synthetic active site happening because the amine and the carboxylic acid are in close proximity to each other. So if we heat them up, as indicated in step 3, we actually can create an amide. Which is pretty cool. So just to give you some names, this is phthalic acid anhydride, or just phthalic anhydride. When you break it up into the amide and the carboxylic acid, it has a fun name. It's phthalamic acid. So we're giving recognition to the amide and to the carboxylic acid. And then when you go through the condensation reaction, we end up creating phthalamide. Now, in this next reaction, we have something really interesting happening. So we have a carboxylic acid, and we have an alcohol and acid. So a carboxylic acid reacting with an alcohol and acid tells us that we're doing a Fischer esterification. Usually we see an excess of alcohol used here, but since the alcohol is in the same molecule, we're going to do an intramolecular Fischer esterification, which is going to end up giving us a cyclic ester. So I want to just talk about how to come up with the structure. We know that if this oxygen attacks here at the carbonyl, we're going to end up with the carbonyl and then all the carbons in between and the oxygen all as part of the ring. So this is going to be a 6-membered ring with the oxygen as one of the members. So we can go through and do some numbering to figure out where everything else needs to go. We're going to have a carbonyl on carbon 1, and then we also need to have a methyl group on carbon 5. Now this is a cyclic ester, which has a cool functional group name, lactone. And we'll talk more about lactones in upcoming sections.